In 1930, physics had a problem. Experiments on beta decay, a process where a neutron turns into a proton, were showing something impossible. The energy before the decay did not match the energy after. A fundamental law of the universe, the conservation of energy, appeared to be broken. It was a crisis. Some of the greatest minds of the time were willing to abandon one of physics' most cherished principles. But a young Austrian physicist named Wolfgang Pauli had a different idea. On December 4th, 1930, he wrote a letter to his colleagues, which he started with the words, "Dear radioactive ladies and gentlemen." He was too shy to present his idea in person. In the letter, he proposed a desperate remedy. He suggested there was a new particle, one that was carrying away the missing energy. This particle had no electric charge and almost no mass. It interacted so weakly with other matter that it would be nearly impossible to detect. Pauli himself was not confident. He wrote, "I have done a terrible thing. I have postulated a particle that cannot be detected." He called it a ghost particle. For 26 years, his idea remained just that, an idea. Then in 1956, a team led by Clyde Cowan and Frederick Rhines finally detected it using a nuclear reactor. The particle, now called the neutrino, was real. Pauli's ghost was found. The discovery revealed something profound about the universe. What we think of as empty space is not empty at all. Right now, trillions of neutrinos from the sun are passing through your body, through this entire planet, as if it were nothing. They are a constant, invisible rain. This story is a good starting point. It shows that our most basic assumptions about reality, like what constitutes nothing or a beginning, can be completely wrong. We are often limited by what we can see and measure. Like the Big Bang Theory, our standard story of creation, has a similar problem. It starts with a point of infinite density, a singularity, but like the missing energy in beta decay, this singularity is a sign that the theory is incomplete. Or it's a point where the laws of physics break down, and just like Pauli proposed a ghost particle to solve a crisis, a new generation of physicists is proposing a radical alternative. They suggest the Big Bang was not a beginning. It was just a transition. The universe, they say, is cyclic. It has no beginning and no end. It bounces. Number 15, the singularity is not a beginning, but a bridge. A single teaspoon of material from a neutron star would weigh about 6 billion tons on Earth. The pressure inside is so immense that protons and electrons are forced to merge, creating a super dense sea of neutrons. A black hole singularity is theoretically infinitely more dense. The Planck length, the smallest possible meaningful unit of length in physics, is about 1.6 x 10 raised to the power of 35 meters. At this scale, our understanding of gravity and space itself collapses. The Big Bang Theory says our entire universe, all the matter, energy, and space-time erupted from a region smaller than that. The standard model of cosmology has a glaring hole right at its start. It is called the initial singularity. The theory works very well describing the universe from a fraction of a second after the Big Bang onward. It explains the expansion of space, the formation of light elements, and the cosmic microwave background radiation. But it cannot describe the moment of the Big Bang itself. According to general relativity, if you run the clock backward, all the matter and energy in the universe converge on a single point of zero volume and infinite density. This is the singularity. This is not a physical description of a real event. It is a mathematical error message. When a theory produces an infinity, it is a signal that the theory has been pushed beyond its limits and is no longer valid. It is like trying to divide by zero. The answer is not infinity. The question is meaningless within the rules of standard arithmetic. The singularity is where general relativity, our best theory of gravity, breaks down. It tells us nothing about what was there or what happened. It is a wall, a point beyond which we cannot see. The Big Bang theory is not a theory of creation. It is a theory of what happened after creation. This is deeply unsatisfying for many physicists and philosophers. An absolute beginning out of nothing is a difficult concept. What caused it? What laws governed this creation if the laws of physics themselves were created in the event? The theory offers no answers. It simply states that at time zero, the universe began. Cyclic universe theories offer a compelling way around this problem. They eliminate the initial singularity altogether. In these models, the Big Bang was not a beginning from nothing. It was a big bounce. The universe existed before the event we call the Big Bang. It was in a state of contraction. It collapsed inward, reached a point of extreme but finite density and temperature, and then rebounded outward. The bounce is the bridge between a previous cosmic era and our own. How is this possible? The key is that general relativity is not the final word on gravity. It is a classical theory. It does not include the effects of quantum mechanics. At the incredibly small scales and high energies of the early universe, quantum effects must have been dominant. A new theory, a theory of quantum gravity, is needed to describe what happens when a universe collapses. While we do not have a complete theory of quantum gravity yet, various approaches like string theory and loop quantum gravity suggest that infinities can be avoided. In loop quantum gravity, for example, space-time itself is quantized. It is made of discrete, indivisible loops. There is a minimum possible size. You cannot squeeze space down to a zero-volume point. As the universe contracts, this quantum nature of space-time creates a powerful repulsive force that eventually halts the collapse and forces it to rebound. The singularity is replaced by a quantum bridge. In brane cosmology, a model derived from string theory, our universe is a three-dimensional brane floating in a higher dimensional space. The big bounce could be caused by the collision of our brane with another. The kinetic energy of this cosmic collision is converted into the matter and energy of a new, expanding universe. The models developed by physicists like Paul Steinhardt and Neil Turok, called the epirotic or pyrotechnic universe, use this mechanism. The bang is not a singular point, but a collision in a higher dimension. The appeal here is profound. It replaces a metaphysical mystery with a physical process. The universe is no longer a one-time event that inexplicably popped into existence. It becomes part of an ongoing, possibly eternal process. The question what came before the Big Bang is no longer forbidden. The answer is another universe. Our cosmos is one in a potentially infinite series of cosmic epochs, each born from the ashes of the one before. It's a universe governed by physical law at all stages, with no need for a supernatural starting gun. It makes the universe a self-contained, self-perpetuating system. Number 14, dark energy is not an end, but an engine. In 1998, two independent teams of astronomers studying distant supernovae made a shocking discovery. They expected to find that the expansion of the universe was slowing down due to gravity. Instead, they found it was speeding up. The discovery was so unexpected that the lead researcher of one team, Saul Perlmutter, spent weeks checking his data for errors before accepting the result. The cause of this cosmic acceleration is a mysterious force called dark energy. It currently makes up about 68.3% of the total energy density of the universe. For this discovery, Perlmutter, along with Brian Schmidt and Adam Riess, received the Nobel Prize in Physics in 2011. In the standard Big Bang model, dark energy has grim implications for the future. The most widely accepted form of dark energy is a cosmological constant, an intrinsic energy of empty space itself. If this is correct, the acceleration will continue forever. Galaxies will accelerate away from each other faster and faster. Eventually, they will cross a cosmic horizon, their light no longer able to reach us. The night sky will become dark and empty, save for the stars in our own local group of galaxies, which will eventually merge and then die out. The universe will end in a big freeze or heat death, a cold, dark, and empty state from which there is no escape. It is a one-way path to cosmic oblivion. The cyclic universe models turn this entire picture on its head. In many of these theories, dark energy is not the agent of a final permanent end. It is the crucial engine that drives the cycle. It is the force that resets the universe for the next bounce. Here's how it works. After a big bounce, the universe expands. For the first several billion years, gravity is the dominant force on large scales. This matter clumps together to form stars and galaxies. But as the universe expands, the density of matter and radiation decreases. The density of dark energy, however, remains roughly constant. Eventually, dark energy becomes the dominant component of the universe's energy budget, and it begins to drive cosmic acceleration. This is the phase we are in now. In a cyclic model, this accelerated expansion continues for an immense period of time, perhaps trillions of years. During this phase, the universe becomes incredibly empty and smooth. The relentless expansion pulls all structures apart, dilutes all matter and radiation to near zero density, and flattens out any remaining curvature in space-time. The universe is effectively wiped clean. All the complex structures and entropy built up over the previous aeon are erased. The universe is returned to a simple, empty, pristine state. This is the key step. It prepares the universe for the next cycle. Once the universe is empty and flat, some mechanism kicks in to trigger a period of contraction. This mechanism varies between different cyclic models. In some versions, the dark energy field itself is not a constant. It is a dynamic field called quintessence. This field could eventually decay, changing its energy from positive pushing space apart to negative pulling space together. This would stop the expansion and begin a long, slow period of contraction. As the universe contracts, it remains smooth and uniform because dark energy has already done its job of ironing out all the wrinkles. The universe collapses back towards a high-density state, not as a chaotic, lumpy mess, but as a smooth, homogeneous whole. This controlled collapse then leads to the next big bounce, which creates a hot, dense state that looks very much like the beginning of our own Big Bang. So, dark energy is repurposed. Instead of being a harbinger of eternal death, it becomes the great cosmic reset button. It is the force that ensures each cycle begins from the right starting conditions, smooth, flat, and empty. It elegantly solves the problem of what happens to all the mess, like black holes and entropy, from one cycle to the next. The dark energy-driven expansion simply spreads it all out so thinly that it becomes irrelevant. It provides a natural, physical mechanism for the universe to be reborn again and again. This transforms our current cosmic epoch from the beginning of the end into just one chapter in a much grander, unending story. Number 13. The universe's unreasonable flatness finds a natural cause. The geometry of the universe can be one of three types: open, closed, or flat. A closed universe is like the surface of a sphere. If you travel in a straight line, you eventually return to where you started. Its geometry is spherical. An open universe is like the surface of a saddle. A straight line journey would see you diverge from your starting point forever. Its geometry is hyperbolic. A flat universe is like an infinite sheet of paper. Parallel lines remain parallel forever. The geometry is Euclidean, the kind we learn in school. Which kind of universe do we live in? The answer depends on its total energy density. There is a specific value called the critical density. If the universe's actual density is greater than the critical density, it is closed. If it is less, it is open. If it is exactly equal to the critical density, the universe is flat. We use the Greek letter omega O to represent the ratio of the actual density to the critical density. So, for a flat universe, O equals 1. Our best measurements, primarily from the cosmic microwave background radiation CMB, show that our universe is astonishingly flat. The WME satellite mission measured O to be 1.02 plus 0.02. The later Planck satellite mission refined this to 1.00 plus 0.005. This means the density of our universe is within 0.5% of the critical density. This presents a huge problem for the standard Big Bang model. A flat universe is an unstable state, like a pencil balanced on its point. Any tiny deviation from perfect flatness at the beginning of the universe would have been magnified enormously over 13.8 billion years of expansion. For the universe to be so flat today, its density at the Planck time 10 raised to the power of 43 seconds after the Big Bang would have had to be tuned to the critical density to an accuracy of 1 part in 10 raised to the power of 62. And that is like measuring the distance to the nearest star to the width of a human hair and getting it exactly right. The standard Big Bang theory offers no explanation for this incredible fine-tuning. It simply has to assume that the initial conditions of the universe were set with this unbelievable precision. This is known as the flatness problem. The mainstream solution to this problem is a theory called cosmic inflation. Inflation proposes that in the first fraction of a second after the Big Bang, the universe underwent a period of hyper-accelerated exponential expansion. It grew from the size of a subatomic particle to the size of a grapefruit almost instantly. This immense stretching would have taken any initial curvature the universe had and flattened it out, just as stretching a small, wrinkled balloon to an enormous size makes its surface appear flat to a tiny observer on it. Inflation solves the flatness problem, but it comes with its own set of issues. The mechanism that starts and, crucially, stops inflation is not well understood. It requires a hypothetical field, the infoton field, with very specific properties that have not been observed. Cyclic models provide an alternative and, some would argue, more natural solution to the flatness problem. They do not require a brief, violent burst of inflation at the beginning. Instead, they use a long, slow period of dark energy-dominated expansion, the very same phase our universe is currently in. In a cyclic scenario, the universe expands for trillions of years under the influence of dark energy before the next bounce. This is an unimaginably long period of slow, steady acceleration. Just like the rapid stretching of inflation, this prolonged stretching has the effect of flattening the universe. Any curvature that might have existed is smoothed out over these vast timescales. By the time the universe is ready to begin contracting, it is already incredibly flat. The contraction phase is also crucial. In the ekpyrotic model, for instance, the contraction is very slow. This slow squeeze preserves the flatness that was established during the long expansion phase. The universe approaches the bounce as a flat, parallel sheet, and it emerges from the bounce in the same flat state. This approach is appealing because it uses the observed dark energy, a known component of our universe, to do the work. It does not require a new hypothetical entity like the inflaton field. The flatness of our universe is not the result of a bizarre one-off event in the first split second of time. It is the natural consequence of a long period of expansion and slow contraction, a process that repeats with every cycle. The universe is flat today because the previous cycle lasted for trillions of years, giving dark energy all the time it needed to iron out the cosmos. It turns an improbable fine-tuning problem into an expected outcome of the cosmic cycle itself. Number 12. The uniform temperature of the cosmos is explained without a rush. The cosmic microwave background, CMB, is the afterglow of the Big Bang. It is a faint light that fills the entire sky, coming from a time about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form. One of the most striking features of the CMB is its incredible uniformity. The temperature of this ancient light is the same in all directions to a precision of 1 part in 100,000. It is a near-perfect 2.725 Kelvin wherever we look. This uniformity presents another major puzzle for the standard Big Bang model known as the horizon problem. The problem is one of communication. For two regions of the universe to have the same temperature, they must have been in thermal contact at some point. Information, in the form of heat, must have had time to travel between them to even out any temperature differences. The maximum speed at which information can travel is the speed of light. When we look at the CMB in opposite directions in the sky, we are looking at two regions of the early universe that were, at the time the CMB was emitted, about 90 million light years apart. However, the universe was only 380,000 years old at that point. There simply was not enough time for a light signal to have traveled from one region to the other. They were causally disconnected, they were outside each other's horizon, so how did they know to have the same temperature? It is like two people who have never met or communicated in any way, somehow wearing the exact same incredibly complex outfit. The standard Big Bang model has no answer. It must assume that the universe was born perfectly uniform for some unknown reason. This is another fine-tuning problem. Cosmic inflation, again, provides the mainstream solution. According to inflation, before the hyperexpansion began, the entire observable universe was a tiny subatomic patch that was in thermal contact. All parts of it were causally connected and could easily reach a uniform temperature. Then, inflation stretched this tiny, smooth region to astronomical sizes. The regions we see on opposite sides of the sky today were once right next to each other, which is why they have the same temperature. Cyclic models offer a different solution, one that relies on time rather than a burst of superluminal expansion. The horizon problem exists because the standard Big Bang model assumes a finite age for the universe and a rapidly expanding early phase. Cyclic models get rid of the finite age. In a cyclic scenario, the universe has a history that stretches back long before the last bounce. The solution to the horizon problem lies in the phase before the bounce. During the long, slow period of contraction, there is an enormous amount of time available for the universe to come to thermal equilibrium. Think of it this way, in the standard model, the universe is like a vast room that was created 380,000 seconds ago, and we are puzzled why two distant corners are at the same temperature when there hasn't been time for the air to circulate. In a cyclic model, the room has existed for trillions of years before the creation event. The air has had more than enough time to mix thoroughly and reach a uniform temperature. The long, slow contraction phase preceding our big bounce ensures that all parts of the collapsing universe are in causal contact. Light signals have ample time, trillions of years, to crisscross the cosmos, smoothing out any temperature variations. The universe that arrives at the bounce is already smooth and uniform. The bounce itself then re-energizes this uniform state, creating the hot, dense, and smooth early universe that we infer from our observations. The appeal of this explanation is its simplicity. It does not require a special, ad hoc period of inflation with a mysterious driving field. It solves the horizon problem by providing the one thing the standard Big Bang model lacks: time. The universe had an almost infinite amount of time before the bounce to get its act together and settle into a state of thermal equilibrium. The uniformity we see in the CMB is not a miracle of initial conditions. It is the legacy of a previous, ancient, cosmic era. Number 11, the origin of galaxies, is seeded by quantum physics, not by chance. The cosmic microwave background is incredibly smooth, but not perfectly so. The Planck satellite has mapped tiny temperature fluctuations in the CMB, variations of just a few millionths of a degree. These tiny ripples are of immense importance. They are the seeds of all the structure we see in the universe today. The slightly hotter, denser regions had more gravity and pulled in more matter over billions of years, eventually collapsing to form the galaxies, stars, and planets. The slightly cooler, less dense regions became the great voids in between. The question is, where did these initial seeds come from? What created these primordial fluctuations? In the standard model with inflation, the answer is quantum mechanics. During the period of inflationary expansion, the universe was dominated by the energy of the inflaton field. Like all quantum fields, it experienced tiny, random quantum fluctuations. These were subatomic ripples in the energy of the field. The incredible stretching of inflation then blew these microscopic quantum fluctuations up to astrophysical scales. They were frozen into the fabric of space-time as genuine variations in density. These are the variations we now see imprinted on the CMB. This is a remarkable and successful prediction of inflation. The specific pattern of these fluctuations, how their strength varies with their size on the sky, matches observations extremely well. This is often cited as the strongest evidence for inflation. However, cyclic models offer a very similar and potentially more refined explanation. They also trace the origin of structure back to quantum fluctuations, but the process happens in a different cosmic setting. In the ekpyrotic model of Steinhardt and Turok, the seeds of structure are generated in the phase before the bounce. As the universe is undergoing its long, slow contraction, the fields that fill the universe are also subject to quantum fluctuation. Just as in inflation, these quantum jitters create tiny variations in energy from place to place. As the universe continues to contract, these fluctuations are converted into density variations that will be present when the universe emerges from the bounce. The key difference is the time scale and energy scale. Inflation happens at an extremely high energy and is incredibly rapid. The cyclic contraction phase is a low energy, very slow process. This difference leads to different predictions for the details of the fluctuations. One of the most important predictions is about primordial gravitational waves. Inflation, being such a violent high-energy process, is predicted to have shaken space-time itself, generating a background of gravitational waves. These would leave a specific signature in the polarization of the CMB, known as B-mode polarization. Finding the signal is a major goal of modern cosmology. Despite years of searching by experiments like BICEP and the Keck array, this primordial gravitational wave signal from inflation has not been found. The limits are getting tighter and are beginning to rule out the simplest models of inflation. Cyclic models, on the other hand, predict that because the contraction phase is so slow and gentle, it would not have produced a detectable background of primordial gravitational waves. The fact that we have not seen these gravitational waves yet is therefore consistent with the predictions of these cyclic scenarios. If future experiments continue to come up empty in their search for this signal, it will be a significant point in favor of the bouncing cosmology alternative. Furthermore, cyclic models can generate the right kind of density fluctuations. The fluctuations must be scale invariant, meaning they have roughly the same strength on all different size scales. Both inflation and cyclic models can achieve this, but through different mechanisms. The ekpyrotic model has been shown to produce a pattern of fluctuations that is also an excellent match to the observed data from the Planck satellite. So, the cyclic approach provides a compelling alternative for the origin of structure. It uses the same fundamental idea-stretching quantum fluctuations, but in a less violent, lower energy context. And critically, it makes a falsifiable prediction that differs from inflation, the absence of a strong primordial gravitational wave signal. The current lack of evidence for such a signal makes the cyclic explanation an increasingly appealing one. Number 10. The arrow of time finds a direction in the cycle's asymmetry. Why does time only move forward? We can remember the past, but not the future. A broken egg never unscrambles itself. This one-way flow of time is one of the deepest mysteries in physics. The fundamental laws of physics, whether Newtonian mechanics, relativity, or quantum mechanics, are all time symmetric. They work just as well running backward as they do forward. Yet, the macroscopic world we experience clearly has a preferred direction for time, an arrow of time. The standard explanation for this is the second law of thermodynamics. This law states that the total entropy or disorder of a closed system always increases over time. The universe as a whole seems to follow this law. It started in a very low entropy, highly ordered state, the hot, dense Big Bang, and has been evolving toward a higher entropy, more disordered state ever since. The arrow of time is simply the direction of increasing entropy. But this just pushes the question back a step. Why did the universe begin in such an incredibly low entropy state? This is a profound fine-tuning problem. For the universe to have started with such a high degree of order by pure chance is statistically absurd. The standard Big Bang model has no explanation for this. It is another initial condition that must be assumed. Cyclic models offer a fascinating potential solution to this puzzle. At first glance, they seem to make the problem worse. If the universe cycles, wouldn't the entropy just build up from one cycle to the next? After a few cycles, the universe should reach a state of maximum entropy heat death, and the cycles should stop. The second law seems to forbid an eternal cycle. However, more sophisticated cyclic models have a clever way around this. The key is that the total entropy of the universe can be reset or diluted during the cycle. The mechanism for this is the long period of dark energy-driven expansion that occurs at the end of each cycle. In a model proposed by physicists Loris Baum and Paul Frampton, the universe expands for trillions of years. During this time, all matter and radiation are diluted to almost nothing. Black holes evaporate via Hawking radiation. The universe becomes a vast, empty, cold space filled only with dark energy and a few stray particles. Entropy, which is associated with matter and radiation, effectively gets spread out to a negligible level. The universe is reset to a very low entropy state. A mechanism then triggers a collapse and a new bounce, starting the next cycle with the requisite low entropy. Another, more subtle idea comes from Roger Penrose's conformal cyclic cosmology CCC. In his model, the entropy is not destroyed, but it becomes irrelevant. Penrose argues that in the far future, when the universe consists only of massless particles like photons, the concept of scale size and time becomes meaningless. The universe forgets how big it is. Through a mathematical transformation called a conformal rescaling, the infinitely large, empty, and cold universe at the end of one aeon becomes mathematically equivalent to the infinitely small, dense, and hot state of a new Big Bang. The crucial part for the arrow of time is that the gravitational field carries entropy too. Penrose argues that while the matter entropy gets smoothed out, the gravitational entropy is low at the Big Bang, a smooth gravitational field, and high at the end of the aeon clumped into black holes. The bounce in his model is asymmetric. It smooths out matter but resets the gravitational field to a low entropy state. This gravitational reset is what gives each new cycle a low entropy beginning, and thus a well-defined arrow of time. In these scenarios, the low entropy of our universe's beginning is not a fluke. It is a necessary outcome of the physics of the cosmic cycle. Each bounce is a reordering event that resets the thermodynamic clock. The arrow of time is not a mystery of creation, but a repeating feature of a universe that perpetually renews itself. This provides a physical explanation for one of our most fundamental experiences of reality. Number 9, the multiverse becomes a history, not a landscape. The theory of cosmic inflation has a strange consequence. In most models, once inflation starts, it never completely stops everywhere. It stops in patches, creating bubble universes like ours. But the space between these bubbles continues to inflate at a furious rate, spawning more and more bubble universes. This process, called eternal inflation, leads to a multiverse, an infinite collection of universes, each with potentially different physical laws and constants. While a fascinating idea, the inflationary multiverse presents a major problem for science. Since these other universes are causally disconnected from ours, we can never observe them or test their existence. It takes the theory out of the realm of testable physics and into the realm of metaphysics. Furthermore, it creates something called the measure problem. In an infinite multiverse, anything that can happen will happen an infinite number of times. This makes it impossible to calculate probabilities. How can we say our universe is typical or likely if there are an infinite number of all possible types? The theory loses its predictive power. Cyclic models offer a different and arguably more grounded perspective on the multiverse concept. Instead of a special multiverse of coexisting but separate universes, they propose a temporal multiverse. The different universes are not elsewhere in space, they are in our own past and future. They are the previous and future cycles of our own cosmos. This is a much more economical idea. It does not require an infinite number of unobservable realms. There is only one universe, but it has an infinite history and an infinite future. The cosmic epochs, or eons in Penrose's terminology, follow one after another in a grand sequence. This has a profound effect on how we think about our place in the cosmos. In the inflationary multiverse, our universe is just one random bubble in an endless, frothing sea. Its properties are a matter of chance. In a cyclic universe, our cosmic epoch is a direct descendant of the one that came before it. There is a cosmic lineage. This could even have observable consequences. While the details of a previous cycle are largely wiped clean by the bounce, some faint traces might survive. Roger Penrose has suggested that massive black hole collisions from a previous aeon could leave faint circular patterns of slightly elevated temperature in the cosmic microwave background of our own aeon. He calls these Hawking points. His team has claimed to have found tentative evidence for such signals, although the claims are highly controversial and not widely accepted by the cosmological community. Similarly, in some bouncing cosmology models, inhomogeneities from a previous contracting phase could leave a subtle imprint on the structure of our universe. The search for these ghosts of a previous universe is an active, albeit challenging, area of research. The appeal of the temporal multiverse is that it keeps cosmology within the realm of potential observation. The other universes are not forever beyond our reach. They are our own history. The evidence for their existence might be buried deep within the data we are already collecting from the CMB and large-scale galaxy surveys. It transforms the multiverse from a speculative, untestable landscape of parallel worlds into a potentially testable history of our own, single, eternal universe. It's a grander, yet more scientifically disciplined vision of the cosmos. Number 8. The philosophical appeal of an eternal cosmos is undeniable. Since the dawn of human consciousness, we have asked two fundamental questions. Where did we come from? And where are we going? For most of human history, these questions were the domain of religion and philosophy. In the 20th century, cosmology provided scientific answers for the first time. The Big Bang Theory gave us a creation story grounded in evidence and mathematics. The theory of stellar evolution and thermodynamics gave us a vision of the ultimate fate of the cosmos. But these answers for many are not entirely satisfying. The Big Bang model posits an absolute beginning. Time and space literally began 13.8 billion years ago. This idea of a beginning out of nothing is a philosophical and scientific stumbling block. It feels like an effect without a cause. It also places our entire cosmic history within a finite time frame. The universe has a birthday. The predicted end is equally stark. In the most likely scenario, the universe will end in a heat death. A cold, dark, empty void. All the complexity, all the life, all the information that has ever existed will be diluted into nothingness. It is a story with a definite beginning and a definite, rather bleak end. The cyclic universe offers a radically different narrative. It is a story without a beginning and without an end. The universe has always existed and will always exist. The event we call the Big Bang was not a moment of creation, but merely a moment of transition, one of an infinite number of such transitions. Our entire 13.8 billion year old cosmic epoch is but a single chapter in an eternal book. This vision has a deep philosophical resonance that echoes many ancient belief systems. Concepts of cyclical time and cosmic renewal are found in Hindu cosmology with its cycles of yugas and kalpas, in Stoic philosophy with its concept of ekpyrosis, a periodic destruction and recreation of the world, and in some indigenous American traditions. The cyclic model brings a modern scientific framework to this ancient intuitive idea that nature moves in cycles, day and night, the seasons, life and death. It removes the awkwardness of a first moment. The question what happened before the Big Bang is no longer nonsensical. The answer is simply the previous cycle. The universe is a self-sustaining system. It does not require an external cause or a creator to set it in motion. It is eternal and self-contained. This perspective can also change our view of our own significance. In a finite universe heading for heat death, all of our achievements are ultimately ephemeral. In an eternal, cyclic universe, things are different. Some have speculated that information might, in some form, be able to cross the boundary from one cycle to the next. If so, the legacy of one universe could influence the next. Even if not, the knowledge that the cosmos itself is immortal, that the dance of creation and renewal will continue forever, lends a sense of permanence and grandeur to existence. This is not a scientific argument in the sense of being provable with data. It is an argument about aesthetic and philosophical appeal. The idea of an eternal, self-perpetuating cosmos, one that has no need for a singular moment of creation, and is not doomed to a final, meaningless end, is for many people a more elegant, complete, and satisfying picture of reality. It presents a universe that is not a fragile, one-off event, but a robust, timeless, and endlessly creative entity. Number 7, Penrose's vision offers a radically elegant mathematical framework. Sir Roger Penrose, a Nobel laureate and one of the world's most distinguished mathematical physicists, has proposed one of the most audacious and elegant cyclic models, conformal cyclic cosmology (CCC). Born in 1931, Penrose made his name working with Stephen Hawking on black hole singularities in the 1960s and 70s. His deep discomfort with the initial singularity of the Big Bang led him to develop his own alternative. CCC is built on a profound insight about the very end and the very beginning of the universe. The model posits that the universe proceeds in a sequence of eons. Each aeon begins with a Big Bang and ends in an infinitely expanding, cold, empty state. The radical idea is that the end of one aeon becomes, through a special mathematical transformation, the Big Bang of the next. Here is the logic. In the very distant future of our current aeon, after trillions upon trillions of years, all stars will have died. All black holes will have evaporated away into a faint bath of low-energy photons and other massless particles through Hawking radiation. The incredibly vast, cold, and nearly empty space filled only with this radiation. At this point, Penrose argues, the universe loses its sense of scale. The only things left are massless particles, which travel at the speed of light. For a photon, time does not pass, and distance is meaningless. In a universe devoid of massive particles that can act as clocks or rulers, the concepts of time and space become fluid. This allows for a mathematical trick called a conformal transformation. This is a geometric transformation that stretches or shrinks things but preserves all angles. Penrose proposes that the infinitely large, empty universe at the end of an aeon can be conformally squashed down. Because there is no scale, this infinitely large space is mathematically identical to an infinitely small, dense space. The end state of one eon smoothly and mathematically connects to the beginning state of the next. The Big Bang of the new aeon is simply the conformally rescaled future infinity of the previous one. This is a beautiful and economical idea. It elegantly solves the singularity problem by replacing it with a smooth mathematical transition. It also has a clever solution to the entropy problem. The second law of thermodynamics, the ever-increasing disorder, seems to forbid an eternal cycle. Penrose argues that the entropy of the universe is dominated by the gravitational field. A smooth early universe has low gravitational entropy. As matter clumps into galaxies and black holes, the gravitational entropy increases enormously. The conformal transformation at the end of the aeon works on the matter and radiation, smoothing it all out. But Penrose's model requires that the gravitational degrees of freedom are reset at the bounce. The Big Bang of each new aeon must start with a very low gravitational entropy, a smooth spacetime. This asymmetry is what drives the arrow of time in each cycle. Most excitingly, CCC makes potentially testable predictions. Penrose argues that traces of the previous aeon could survive the transition. He suggests that supermassive black hole mergers in the late stages of the previous aeon would have released enormous bursts of gravitational waves. These waves would pass into our aeon, creating faint circular patterns of slightly lower or higher temperature in the cosmic microwave background. Another prediction involves Hawking points. These would be the points on the CMB where the Hawking radiation from the evaporation of an entire supermassive black hole from the previous eon enters our aeon. These would appear as small, extremely hot spots in the microwave sky. Penrose and his collaborators have analyzed data from the MAP and Planck satellites and claim to have found evidence for both types of signals. These claims are highly controversial. Most cosmologists believe the patterns they have found are likely just random fluctuations in the CMB, not evidence of a past universe. The statistical significance is debated. However, the fact that the theory makes such specific, searchable predictions is a major point in its favor. It is not just a philosophical idea, it is a scientific hypothesis that is being actively tested. The elegance of its mathematical foundation and its potential for observational verification make conformal cyclic cosmology a truly compelling vision. Number 6. The cosmological constant problem is softened. One of the most embarrassing and profound problems in modern physics is the cosmological constant problem, also called the vacuum catastrophe. Quantum field theory, our incredibly successful theory of particles and forces, predicts that empty space should not be empty. It should be fizzing with a sea of virtual particles that constantly pop in and out of existence. These particles should have energy. When physicists try to calculate the energy density of this vacuum, the number they get is absurdly large. The predicted value for the vacuum energy density is about 10 raised to the power of 121 times larger than the value we actually observe for dark energy. This is the single worst prediction in the history of physics. To put this number in perspective, it is a 1 followed by 121 zeros. If the vacuum energy were really this large, its repulsive gravitational force would have ripped the universe apart in the first fraction of a second. Stars and galaxies could never have formed. The fact that we exist proves the calculation is wrong, but no one knows why. Physicists have had to assume that there is some unknown physical principle or cancellation mechanism that reduces this enormous value down to the tiny non-zero value we observe today. It is a fine-tuning problem that makes all other fine-tuning problems look trivial. Cyclic models do not solve the cosmological constant problem completely. No theory currently does. But they can offer a different perspective that makes the problem less acute. The problem arises because we are trying to calculate an absolute fundamental value for the vacuum energy. In a cyclic universe, the effective value of the cosmological constant might not be a fixed fundamental number. It could be a field that changes over time. In many cyclic models, the role of dark energy is played by a dynamic scalar field, often called quintessence. The energy density of this field can change as the universe evolves. The value we measure today is not a fundamental constant of nature, but simply the value this field happens to have during our current cosmic epoch. This opens up the possibility of a selection mechanism. If the universe has gone through a vast number of cycles, perhaps there is a process that causes the value of the dark energy field to decrease with each cycle. A mechanism proposed by Steinhardt and Turok suggests that the value of the field could relax towards zero over many, many bounces. Our universe, after a long history of previous cycles, would naturally find itself in a state where the cosmological constant is very small. This approach does not explain why the fundamental value predicted by quantum mechanics is wrong, but it provides a physical reason for why the observed value is so small. It is not a random accident. It is the result of a long evolutionary process. Another idea is that the value of the cosmological constant is tied to the size and age of the universe in each cycle. The universe might have a feedback mechanism. In cycles where the cosmological constant is large, the expansion is too rapid, and the conditions are not right for the cycle to complete and a new bounce to occur. Only cycles with a small, just right value for the cosmological constant are stable and can repeat. Over an infinite history, these are the only types of cycles that would persist. While these are still speculative ideas, they reframe the problem in a helpful way. Instead of a static, inexplicable fine-tuning of a fundamental constant, the smallness of the cosmological constant becomes a dynamic feature of an evolving ancient universe. It is a problem to be solved with cosmology and dynamics, not just particle physics. The cyclic framework provides a much larger canvas on which to work, allowing for evolutionary or selection-based explanations that are simply not available in a universe with a single, absolute beginning. This makes the daunting 121 orders of magnitude discrepancy seem less like a fundamental error in our understanding and more like a puzzle about the long-term history of the cosmos. Number 5, the end of the universe is averted. The standard cosmological model predicts a definitive, and rather lonely, end for our universe. Assuming dark energy is a cosmological constant, the future is one of endless, accelerating expansion. This leads to a scenario known as the Big Freeze, or heat death. The sequence of events is bleak. In about 100 billion years, all galaxies outside our own local group will have accelerated beyond our cosmic horizon, their light forever unable to reach us. The sky will be dark. In a few trillion years, star formation will cease as all available gas is used up. The existing stars will one by one burn out, becoming white dwarfs, neutron stars, and black holes. In about 10 raised to the power of 15 years, planets will be ejected from their orbits or spiral into the dead stellar remnants. Over much longer timescales, from 10 raised to the power of 30 to 10 raised to the power of 40 years, protons themselves may decay, causing all ordinary matter to dissolve into a sea of radiation and leptons. The final stage is the era of black holes, but even they are not eternal. Over unimaginable timescales, from 10 raised to the power of 67 years for a stellar mass black hole to 10 raised to the power of 100 years for a supermassive one, they will evaporate through Hawking radiation. The final state of the universe will be a cold, dark, featureless void filled with a sparse, ever-diluting gas of photons, neutrinos, and other fundamental particles. The universe will have reached a state of maximum entropy. No more work can be done. No more complexity can arise. Time itself will lose its meaning. It is a final, irreversible end. Another, more violent possibility is the Big Rip. If dark energy is a more exotic form called phantom energy, its repulsive force will grow stronger over time. This would lead to a runaway expansion that would tear everything apart. In a finite time, it would overcome the gravitational force holding galaxies together, then the electromagnetic force holding atoms together, and finally the strong nuclear force holding atomic nuclei together. The fabric of space-time itself would be ripped apart. The cyclic universe model offers a profound alternative to these terminal fates. It posits that the universe is not on a one-way trip to oblivion. The end is not the end. The expansion phase we are in now is just one part of a larger cycle. The universe will not expand forever. In these models, the current era of accelerated expansion is a necessary step to prepare for the next bounce. It smoothes and flattens the universe, but eventually this phase will end. Some mechanism, perhaps the decay of the dark energy field or the influence of extra dimensions, will cause the expansion to halt and reverse into a period of slow contraction. This contraction will lead to a new big bounce, a new hot, dense phase, and the birth of a new cosmic aeon. The universe will be reborn, new stars will form, new galaxies will cluster, and perhaps new life will emerge. This is a deeply optimistic and appealing vision. It replaces a future of eternal coldness and death with one of eternal renewal and rebirth. The cosmos is not a finite resource that is slowly running down. It is a sustainable, self-perpetuating system. This has important philosophical implications. It suggests that complexity, structure, and perhaps even life are not fleeting accidents in a universe doomed to decay. They are recurring features of a cosmos that is endlessly creative. The universe is not dying, it is merely resting and preparing for its next act. The laws of physics do not lead to an ultimate dead end, but to an endless cycle of cosmic death and resurrection. The story of the universe is not a tragedy, it is an epic with an infinite number of sequels. Number 4, string theory and M theory find a natural cosmological home. String theory is one of the leading candidates for a theory of everything, a unified theory that describes all forces and particles of nature, including gravity. It proposes that the fundamental constituents of reality are not point-like particles, but tiny, one-dimensional vibrating strings. Different vibrations of these strings give rise to the different particles we observe. A key feature of string theory is that it requires extra spatial dimensions to be mathematically consistent. Most versions of the theory require a total of 10 spacetime dimensions, 9 space and 1 time. Since we only experience 3 spatial dimensions, the extra ones must be hidden, perhaps compactified, or curled up into a tiny size, too small to detect. In the 1990s, these different string theories were unified into a larger framework called M theory, which posits 11 spacetime dimensions. The M theory also introduces new objects called branes, short for membranes, which are higher dimensional surfaces. A 0 brane is a point. A 1 brane is a string. A 2 brane is a plane, and so on. This theoretical framework provides a natural setting for cyclic cosmology. One of the most prominent cyclic models, the ekpyrotic model, was born directly out of M theory. It was proposed in 2001 by Paul Steinhardt, Justin Khoury, Bert Overoot, and Neil Turok. In this model, our 3-dimensional universe is a brane floating within a higher dimensional space called the bulk. Parallel to our brane, separated by a tiny gap in the 4th spatial dimension, is another brane. The Big Bang in this picture was not a singularity, it was the result of these 2 branes colliding. The cycle works like this. The 2 branes start out empty, cold, and parallel. A force between them related to the dark energy field pulls them together. They collide. The immense kinetic energy of this collision is converted into the hot soup of particles and radiation that we identify as the Big Bang. This happens all over the surface of our brain, so the universe starts out hot and uniform everywhere at once. After the collision, the branes bounce apart and begin to separate. As they separate our universe, our brane expands, cools, and forms structures like galaxies, just as in the standard Big Bang model. Eventually, dark energy dominates, smoothing everything out and pulling the branes apart for trillions of years. Then the cycle repeats. The force pulls them together again for another collision. This brane world scenario has several appealing features. It provides a physical mechanism for the bounce, replacing the mysterious singularity with a collision of branes in a higher dimension. All the calculations are done within the framework of M theory, a well-defined, though not yet complete, fundamental theory. It also offers a natural explanation for why our universe is 3-dimensional. We are simply confined to live on a 3 brane. It also suggests that gravity might be different from the other forces because it is a property of the higher dimensional bulk, while the other forces, electromagnetism, nuclear forces, are stuck to our brane. This could explain why gravity is so much weaker than the other forces, a long-standing puzzle in physics. The ekpyrotic model makes specific testable predictions that differ from inflation. As mentioned before, it predicts no detectable primordial gravitational waves. It also predicts a different pattern for non-Gaussianities, which are subtle three-point correlations in the CMB fluctuations. Future, more precise measurements of the CMB could distinguish between the inflationary and ekpyrotic scenarios. The connection to string M theory gives the cyclic model a strong theoretical foundation. It is not just an ad hoc idea, but a cosmological scenario that emerges naturally from our best attempt at a fundamental theory of quantum gravity. It shows how the abstract and esoteric ideas of extra dimensions and vibrating brains can have direct consequences for the history and future of the very universe we inhabit. Number 3, the model is falsifiable and makes unique predictions. A scientific theory is only useful if it can be tested. It must make specific predictions about the world that can be verified or, more importantly, falsified by experiment and observation. A theory that cannot be proven wrong is not science, it is dogma. For a long time, cyclic models were criticized as being more philosophical than scientific. They offered an elegant picture, but seemed to lack sharp, testable predictions that could distinguish them from the standard inflationary Big Bang model. That has changed significantly in the last 2 decades. Modern cyclic models like the ekpyrotic universe and conformal cyclic cosmology now make a suite of unique and falsifiable predictions. The most important of these concerns primordial gravitational waves. As discussed, the violent, high-energy expansion of cosmic inflation is predicted to have created a background of gravitational waves that would leave a faint, swirling pattern B mode polarization in the cosmic microwave background. The strength of this signal is directly related to the energy scale of inflation. In contrast, the slow, low energy contraction phase in ekpyrotic style models would produce a gravitational wave signal that is far too weak to be detected. This presents a clear fork in the road. The search for this B-mode signal is a top priority for cosmologists. Experiments like the Simons Observatory and CMB-S4 are being built to search for it with unprecedented sensitivity. If they find the signal, it would be a major victory for inflation and a serious, perhaps fatal, blow to these cyclic models. If, however, after years of searching with ever more powerful instruments, the signal is not found, it would strongly favor the cyclic alternative. This is a clear, unambiguous test. Another area of prediction is the spectral index and non-Gaussianity of the CMB fluctuations. The spectral index NNRs measures how the strength of the density fluctuations changes with their physical size. The simplest inflationary models predicted a value very slightly less than 1. Observations from the Planck satellite have measured N-on-1s to be about 0.965, a stunning success for inflation. However, cyclic models have also been shown to be able to produce a value in this range. The key to telling them apart may lie in more subtle statistical properties. Non-Gaussianity refers to deviations from a purely random bell curve distribution of the temperature fluctuations. Different models of the early universe predict different types and amounts of non-Gaussianity. While inflation typically predicts a very small level, some cyclic models predict a larger, potentially detectable signal with a specific shape or configuration. Current measurements have not found any significant non-Gaussianity, which puts pressure on some models, but future surveys could reveal a subtle signal that points toward one theory or the other. Then there are the more exotic predictions from Penrose's CCC, such as Hawking points and concentric circles in the CMB. These are specific, searchable signatures. While the initial claims are controversial, the search continues. Finding such a signal would be revolutionary. Failing to find it after a thorough search would weaken the case for that specific model. The ability to make these kinds of concrete, risky predictions is what moves the cyclic universe idea from the realm of speculation into the arena of testable science. It is no longer just an appealing alternative on philosophical grounds. It is a genuine scientific competitor to inflation with its own set of strengths, weaknesses, and most importantly, observational consequences. The next decade of cosmological observation promises to be a crucial testing ground that could provide evidence to support or rule out these two competing visions of our cosmic origins. Number 2, the fine-tuning problem becomes less puzzling. The universe appears to be exquisitely fine-tuned for the existence of life. A number of the fundamental constants of nature, the strength of gravity, the mass of the electron, the value of the cosmological constant have values that seem to be just right. If any of them were even, slightly different, the universe would be a sterile place. For example, if the strong nuclear force were just 2% stronger, all hydrogen would have been rapidly converted into helium in the Big Bang, and there would be no water or long-lived stars like our sun. Well, if it were 0.5% weaker, deuterons would not be stable, and the nuclear chain reaction that powers stars could not begin. If the gravitational constant were slightly larger, stars would burn out too quickly for life to evolve. If it were smaller, stars might not ignite at all. In the standard Big Bang model, these constants are simply given. They are brute facts about our universe with no underlying explanation. The theory requires us to accept that we live in a universe that won the cosmic lottery, with all the dials set to the life-permitting values by sheer incredible luck. This is the fine-tuning problem. To get around it, many cosmologists appeal to the inflationary multiverse. In this view, there are an infinite number of bubble universes, and the constants of nature vary randomly from one bubble to the next. In most of these universes, the constants are wrong for life. We, naturally, find ourselves in one of the rare universes where the constants are right, because we couldn't exist anywhere else. This is an explanation known as the anthropic principle. The anthropic principle is unsatisfying to many scientists. It feels like giving up on finding a deeper physical explanation. It also relies on the existence of an unobservable multiverse. Cyclic models offer a potential alternative to the anthropic explanation. They provide a framework where the constants of nature might not be fixed forever. It is possible that with each bounce, the values of the fundamental constants could change slightly. The universe could have a mechanism for learning or evolving over many cycles. This idea, sometimes called cosmological natural selection, was first proposed in a different context by the physicist Lee Smolin. Applied to a cyclic universe, it suggests that universes with successful parameters, those that allow for long-lived stars, the formation of black holes, and an eventual bounce, are the ones that will have the most offspring cycles. Cycles with parameters that lead to a quick death or an eternal expansion without a bounce would be evolutionary dead ends. Over a vast number of cycles, the universe could naturally evolve towards a set of physical constants that are stable and life-permitting. The values we observe would not be a random accident, but the result of a long process of cosmic evolution. For this to work, there would need to be a mechanism that allows information about the constants to be passed from one cycle to the next, and a mechanism for slight variations to occur at each bounce. This is highly speculative and the physics is not well understood. However, some ideas from string theory, with its landscape of possible vacuum states, could provide such a mechanism. Each bounce could reset the universe into a new state from the landscape, with slightly different effective physical laws. Even without a full evolutionary model, the cyclic framework simply provides more opportunities. A single one-shot universe makes fine-tuning look like a miracle. A universe that has existed for an infinite amount of time and gone through an infinite number of cycles makes the emergence of a life-permitting phase seem much less surprising. Given enough time and enough chances, even rare configurations will eventually occur. The cyclic model, therefore, lessens the mystery of fine-tuning. It replaces the need for a multiverse of separate spatial universes with a history of temporal universes. It opens the door to dynamic evolutionary explanations for the laws of nature, transforming what looks like incredible luck into a potential outcome of a long and ancient cosmic history. Number 1, it is a more complete and self-contained cosmology. The ultimate goal of cosmology is to provide a complete and self-contained description of the universe. A successful theory should explain not just how the universe evolved, but also where its initial conditions came from and what its ultimate fate will be. It should be governed by physical laws at all times and at all scales, without any need for special, unexplained starting points or metaphysical interventions. By this standard, the Big Bang model, even when augmented with inflation, is incomplete, and it has a beginning that it cannot explain the initial singularity. It has initial conditions that it must assume, the extreme flatness, homogeneity, and low entropy of the early universe. It has fundamental constants that appear fine-tuned without any physical reason. It relies on a hypothetical inflaton field whose properties and origin are unknown. And it predicts a future that is either a cold final death or a violent final rip. It is a powerful theory, but it leaves the biggest questions unanswered. The cyclic universe as an alternative offers a vision that is far more complete and self-contained. It is a framework that attempts to answer the why questions that the standard model cannot. It eliminates the initial singularity. The universe has no beginning and no end, so the question of what came before is answered. The universe itself is the answer. It provides physical mechanisms for the initial conditions. The flatness and homogeneity of the universe are not assumed, but are the result of a long period of dark, energy-driven expansion in the previous cycle. The low entropy of the Big Bang is a consequence of the reset that occurs at each bounce. It provides a new context for understanding fine-tuning and the cosmological constant. These are not necessarily fixed, God-given numbers, but could be dynamic quantities that have evolved over countless cycles. It grounds its mechanisms in more fundamental theories. Models like the ekpyrotic universe are built upon the foundation of M-theory, our best candidate for a theory of everything. This connects cosmology directly to the search for the ultimate laws of nature. It proposes a future that is not a final end, but a new beginning. The universe is not a one-time event, but a sustainable, eternal process of renewal. Of course, the cyclic theory is not without its own major challenges. The physics of the bounce itself, the moment of highest density, is not fully understood and requires a complete theory of quantum gravity. The specific mechanisms that trigger the turnaround from expansion to contraction are still speculative. And, most importantly, the theory needs to be backed up by definitive observational evidence. Nevertheless, the appeal of the cyclic model lies in its ambition. It seeks to build a cosmology that stands on its own without unexplained starting points or fine-tuned parameters. It paints a picture of a universe that is eternal, evolving, and governed by a single, coherent set of physical laws from start to finish, because there is no start and no finish. It is a universe that does not need a cause outside of itself. It is a universe that is, in the truest sense of the word, complete. This pursuit of a deeper, more comprehensive, and more rational understanding of existence is what drives science forward. The cyclic universe may or may not be the correct description of reality, but it represents a profound and compelling step toward that ultimate goal.